So the last question 10.4 says, for which values of k will minus x minus 1 cubed plus 6x minus 1 squared minus k equal to 0 have one negative and two distinct positive roots? Now it's important to analyze that this is within the same question. So this is somehow related to h of x. This is a new function. We can call it k of x. And k of x is achieved by shifting h of x 1 unit to the right, which is seen by that minus 1. And then there is some other k kind of shift that we need to talk about. But for now, I'll only analyze this. So if we were to shift this function 1 unit to the right, we would have minus, whenever we see x, replace it with x minus 1 cubed plus 6 x minus 1 squared, like that. That's what you would have, and that's where they get that function from. So I've briefly sketched it over here, and this will be our new y-axis over here, and this will now be at 1, and you can basically think about it as nullifying this old y-axis. That's what happens when you shift this function 1 unit to the right. This is what is obtained. I could also draw another representation here, and that would look something like this. And our function has been shifted by 1 unit to the right, so it no longer intercepts there, but here. So it's not really drawn to scale, but something like this, whereas this is 1, and this is our y-axis, and this is our x-axis. So shifting our graph 1 unit to the right gives us this graph. Now we need to find where we can draw k. Now k is just a straight line. K is just a straight line, and we are asking ourselves, what are all the possible values of k that we could have such that when we move it around, we get 3 intercepts on our graph, and these 3 intercepts, 1 will be negative and 2 will be distinct and positive. So if I analyze it where it's currently at, I'm getting 1, 2, 3 intercepts, but the problem is all of them are positive. So in order for one of them to be negative, our line, our straight line, which is y is equals to k, this line needs to be above this point over here, because at this point one of them is 0 and the other are 2 positively distinct. So anything greater than this point here could be that. We see that there is a negative 1 here and 2 positive on this side, and this continues up until that maximum over there. If we cross this point, we no longer get 2 distinct. Even if we're on this line, we are getting 1, or we're getting 2 of them here, but they are 2 and equal. They are not 2 and distinct. So we need to be strictly below this line and strictly above this line as well. So within this region bounded by these 2 blue lines, that's the region we need to describe. We already know what the maximum is because this point is given as 4 as to 32. So we know k cannot be greater than 32, which is that turning point there. But we now need to find out what that y-intercept is over here. So to find that y-intercept, we make x 0 in this equation to find what the y-intercept will be. And that we can find like this. Making x 0 here, we're going to have minus 1 cubed plus 6 minus 1 squared. This gives us 7. So it means that point over there is 0 as to 7, which means k has to be between 7 and 32. and you can write that as k has to be between 7 and 32. So k is greater than 7 but smaller than 32. And notice I'm not putting the or equal to, because our regions need it to be strictly greater than or strictly less than for them to satisfy the condition given. And you could also represent your answer as k is an element of all numbers between 7 and 32. Notice I'm not using the square brackets because the square brackets include the bounded regions. So this would be your answer.